Welcome back. Today we will speak about basic electronic components. So we have done the resistor, and now we will speak about another fundamental component which is called capacitor. So here you see something. It's a diagram which is something in 3 dimensions. So you see those two things, this one and this one, are two parallel plates. So they are like this, they are parallel each other. They are made of a good conductor material, so let's say a metal. They have a metallic wire, another good conductor material. And here we connect a battery. So we need to discuss this a little bit. So this is not a schematic diagram, but let's say almost. So it will be a 3D drawing, but let's say it's also a schematic diagram. So in what sense? In the sense that this piece of electric conductor is an ideal conductor. So it's a conductor having zero resistance. So from the point of view of this circuit, for us it would be the same of having the battery attached directly here. So all this length, to be more clear, in this diagram is not existing. So it can be any length. For us, when we see such kind of lines, it means just that this point here is connected to this, no matter the length, no matter the shape of the path. So what happens here is something different. We have a constitutive law that tells us the behavior of this device, which is called capacitor. And the constitutive law is this one. Q, so the charge deposited on the plates, so positive charge and negative charge, is equal to a constant C, we call this constant capacitance, multiply the voltage. So what this law is telling us is that if we apply a battery with a certain voltage V, then we have a charge exiting from the battery, and this charge would be displaced on the plates. So why it's like this? Because there is an electric field between those two plates. This electric field is due to the fact that we apply a battery to those two plates. So the negative charges here are attracted by the positive side here above, and this is why they want to move like this. So in the beginning the process is like this: you attach the battery, some negative charge, which are electrons, will exit from the battery, attracted by this positive side just in front of it because of this Coulomb attraction, and then at a certain point this phenomenon will stop. When it will stop? When those plates will be full of charges, so in a way that they cannot contain any more charges. So this has to go with the surface. So the bigger the surface, the bigger the charges, the amount of charge that you can deposit on it for a given voltage, and it's inversely proportional. The charge is inversely proportional to the distance of the plates, because for a given voltage applied to the plates, the smaller the distance, the bigger the electric field. Remember that the electric field was minus the gradient of the voltage. So in one dimension, let's say in this dimension, the electric field is minus the derivative of the voltage with a distance. So for a given delta V, if you take a smaller delta x, the electric field is bigger. So then we can also do another thing. We can consider this thing. So now we don't have to get confused with this. So these are two different things. So now this letter E stands for energy. We can compute how much energy there is in this system, and it turns to be equal to this thing. We don't demonstrate this calculation, but we just comment it. So we can say that the capacitor is a sort of storage of energy in terms of electric field that you can feel between the plates. So the capacitor is a storage of energy in form of electric field. So this thing is important here, and it will be more important when we will study circuits in so-called sinusoidal regime, because it will give us an insight about the behavior which is similar to the behavior of the resistor, but now with a different constitutive law. Then another basic component is called inductor. So inductors, most of the time they are like this. You see this shape? So this is a real inductor. So there is a piece of metal, it's turned like this as a coil. So inside it's hollow. This piece of metal has an insulator. So there is a layer here. This red or let's say dark varnish is insulating all the loops each other, so they are not short-circuited like this. They are very close each other, they are also touching, but they are not in electrical contact. So the electrical contact stays only here where these two terminals are exposed. You see they have a different color. Okay. So for this component, we can think of doing one thing. We can try to make some electric current flowing in it. So it will flow like this, and then it will exit from here. Let's say this current is I. So it means that this is connected into circuit. And what we can do is while we make this current flow in it, we measure the voltage across this component like this. We call this voltage V. And we can verify this thing experimentally, let's say, that the voltage V across this component is not like the resistor proportional to the current, but it's proportional to the variation of the current in time. And the coefficient of proportionality is called L, which is called self-inductance. So this is an inductor, and the property of an inductor is the inductance. So for inductors, it is a little bit more difficult to understand a relationship between the geometrical properties of an inductor and the coefficient of self-inductance. So here we have an example for a so-called thin and long inductor. And what we can see, we can comment this thing. We can see that the inductance is proportional to an area, which is the cross section of the inductor, and inversely proportional to the length. So for us now, for the moment, it is important to remember this proportionality to an area. N is the number of turns. So to make a one-turn example, so if we have a circuit like this, and then we put current flowing in it, so this arrows is indicating the direction of the current. So for us it is important to remember that the bigger the area, the bigger the inductance. This would be useful when we will speak about electromagnetic noise induced in a so-called ground loop. We just keep this for later. Another thing that we can do, similar to what we did for the capacitor, is to calculate the energy of this system. And we have this thing, again, we don't demonstrate this, it's not so straightforward. But we just commented to say that in a way which is analogous to what happened in the capacitor, this inductor here is also a sort of storage of energy in the form not of an electric but of a magnetic field generated by the current I flowing in it. So capacitor and inductors are objects that in different ways can accumulate and release electric energy. Now we have to jump a little bit further, because you can imagine that if you have an electronic device, a modern, let's say, electronic device, like this one for instance, or other things, the tablet itself, so you don't see only those so-called fundamental components. Most of the time components are miniaturized, so they can be very small. They can be also smaller than you think, because for instance this component here, which is a microchip, so we see it as a piece of plastics with some legs, I mean those contacts, gray contacts, which are made in metals. We don't know what's inside this thing, but I can swear it's full of things, very miniaturized, so the so-called microchips made in silicon. So most of the time in real life it's not possible to go to an elementary level of capacitor, inductors, resistors, and also we will see diodes and transistors. These things are very complex. So manufacturers give us what is called the datasheet of the component. So this is an example of datasheet. It's a datasheet of a transistor. This is the transistor. So what is it? It's a document where you see some characteristic of interest. So at certain point I spoke about black boxes. So things like that. Representation like this, where you have inputs, outputs, and something in it. So this thing is described by behavior description, not by electric circuits. For instance, here you see it tells you something like the maximum voltage, the maximum current, the maximum power dissipated, and so on. So you have a model and you have to play with this model. You can't go further in real life in electronics with those commercial devices. So here you have another example. is connected to this previous example of this transistor. So this is a so-called SPICE model. SPICE is an acronym of a commercial software for simulating electronic circuits, and they give you this type of description. It's a code, so it's not very human readable, but kind of, with a lot of parameters that will describe the behavior of this component. So it doesn't give you a schematic diagram with resistor, capacitor. It just gives you a piece of code that you have to plug in a piece of software in order to simulate it. So this is an example of how things are done in real life in electronics. We are at the abstraction layer, which is above the one of the physical fundamental components. So here you have another example of real life electronics. So what you see here on the right is a so-called printed circuit board, which is this kind of thing. So you see, this is the printed circuit board. Populated with many little things which are called electronic components. So everything is modular. For instance, I can show you some components. So here you have some capacitors and also some inductors. So for instance, this is how a capacitor looks like in real life. So it's a small box with something in it and two terminals, and the only thing we know about it, now it's a very simple information because it's also written here, it's the value of its capacitance, which in this case, I don't know if you can see, is 330 nanofarads. So this is another capacitor, for instance. You see, this one is bigger. Here we have a couple of inductors of different shape. So this is an example of real-life electronic components. So printed circuit boards are made in fiberglass. They have some tracks, like those tracks here. They are made in copper. They are blue here because then there is a varnish that will protect them against the atmospheric agents. But all those tracks are very good conductors, and they create a sort of, let's say, a city where the components are the buildings, and they are connected one each other with the roads where the electrons will flow. They are also perforated in some time, like this time. You see that some components can pass through the board, like this stripe of connectors, or like the terminals of this microchip. So these are called the pass-through component, or PTH, pass-through hole component. While some others, like the small ones, like this one, they don't pass through the board, but they are surface mounted. These are called surface mounted components, or surface mounted devices, SMD components. And here you have an example of a workstation to design circuits. So everything is done this way nowadays. So we have to switch from physics to electronics, and because things quickly and easily get complicated, we need to talk about a workflow. We can't do on the fashion of physicists, sorry for the physicists, we can't solve equations. There are literally too many equations, too many things are connected together. So the problem of electronics is that the complexity increases a lot quite quickly. So we have to break this complexity somehow. So when we design a circuit, for instance, the first thing we need to do is to define what we want. That means that we have to write down specifications. Like for instance, I want to design a thermostat to control the temperature of this room. It's not enough. I have to say probably what is the target temperature, what is the variation I can tolerate, which is the timing that I can set for starting from a certain level of temperature and reaching the target temperature. Probably I need also to mention the dimensions of the room, because if the room is small, then the thermostat will be much smaller, and then if the room is very big, then I need a different system of heating and cooling to control the temperature. So I need to specify all these things. Then if we stick to this example of temperature control of a room, I can go further and I can start speaking about how to abstract all those properties into functional blocks, which means synthesis. For instance, after having reasoned a little bit, I can understand I will probably need a sensor of temperature, a kind of actuator in order to heat or cool the room. Then I maybe need a controller for all these things, because I need to calculate this heating and cooling curve and such kind of things. Once I made a block diagram, I have to build each block. So we are in this phase, implementation. And it's a good idea to try to divide things as much as we can in elementary building blocks, in the sense that they only interact each other through their inputs and outputs without being affected each other so much. So we want to have blocks that somehow are isolated each other, because this makes our life easy for another thing, which is the validation. So we have to test each block. So we are not completely sure that all these things will work from the very beginning. Maybe we have to go through a process of trial and error and refinement in order to reach the good state for our circuit, which means that we probably need to pass through these things in a cycle. It might be that we ask something unrealistic from the very beginning, like I want to set the temperature in this room starting from 0 Celsius to 30 Celsius in 1 millisecond. That specification is unrealistic. It's impossible to do this. So if we reach this impossibility, then we probably have to relax some specification and so on. And last but not least, we have to document what we do. For simple things, for very simple things, it might be not necessary, but I swear you that this thing is something that easily can create a lot of problems. So if you don't document what you do, because maybe sometimes you do something that works, and then you put it back, and then after a month you go back and you see what you did, and you ask, but okay, it works, but how could I do it? So why it works? I'm not sure how it works. So it's better to have in mind this idea of documenting things. And another important thing is what is written here, and also here with this funny picture. So you have to think of designing things for testability. So if you think that at a certain point, for instance, the speed for setting the temperature in your room is important, because maybe you say, okay, I have a meeting in that room, I can't ask to the people in that room to wait 12 hours before the temperature in the room reaches the target point of, I don't know, 22 Celsius. So if you identify something which is important to be tested, you have to provide in your system the tools in order to test that thing. So here you see a funny example. So this guy is asking if love is in the air, and this is the answer. So according to his opinion, the air is made of nitrogen, oxygen, and whatever. So he's not using the good tools to test its original question. So it's important to understand this thing. Okay, so now we conclude this first part of the class with a list of common things and tools, I mean things that you can easily find or you expect to be present in an electronic workshop. So you need a couple of basic instruments, for instance a multimeter. Here we have an example of multimeter. So it's like this. Usually it's a handheld tool. So you turn it on. We will speak better into details of this. So it has many functions. It can measure voltages, currents, also resistances. So it looks like this. Then you might want to have a variable regulated power supply. So a couple of days ago I repaired my own power supply, which is this thing here. I put also a video on YouTube. So these are such kind of things. This is regulated, but unfortunately for me it's quite old, it's not variable. Then you probably need an oscilloscope. So those can have different shapes. I have a small one here. It's like this. Actually, it's a combination of oscilloscope and multimeter. So you see the terminals of a multimeter, but if I press a button, I can switch it from the function of a multimeter. For instance, this is a voltmeter, to another function of oscilloscope. You will see this in better details. And then you probably need a computer with some printed circuit board CAD, so this software that allows you to do electronics. So here I don't read all these kind of things because they are let's say popular. I mean soldering iron, like this kind of thing, in order to solder the circuits. A soldering sucker, which is this thing here, which is used to remove the solder from circuits if you need to remove a component. Pairs of tweezers, cutters, clippers, screwdrivers, whatever. And then we will speak better about all these materials which are necessary to build circuits.